Hello and welcome to this webinar titled, Is Excel Hindering Your Engineering Projects? My name is Shola Slough. I'm Technical Specialist at Maplesoft, and presenting with me today is my colleague Stephen Forrest, Product Manager for Maple. We'll start by looking at how extensively Excel is being used today and discuss why it is not an appropriate tool for engineering projects. We'll then look at some requirements for suitable tools for engineering calculations, and then go on to show how Maple meets all these criteria and outperforms Excel in every way. Now, every engineer has ready access to Excel. Most computers have Microsoft Office installed, so you inherently have Excel right there at your fingertips. So it's so easy to open it up and start putting in some numbers into a worksheet and doing some basic calculations. Then you may share that worksheet with some colleagues and someone makes a change that introduces an error, and 3 months down the line the project team realizes they've been using incorrect numbers all this time. Now, while Excel has many uses, it is fundamentally a spreadsheet. That is, an interactive application for organizing and analyzing data in tabular form, or a computer program that calculates numbers and organizes information in columns and rows. And right there we can see that engineering calculations don't fall under this restrictive description of tabular form and columns and rows. And when working with Excel, equations and formulae are hidden from view. The calculations are performed behind the scenes, and there's no easy way to follow the flow of information. So where are input values coming from? Where are the results of a calculation being used? What assumptions were made and what values were changed along the way. And all of this leaves plenty of room for errors. Spreadsheet errors are notoriously difficult to spot, and in some cases can have dire consequences. Now, you may be aware of some recent spreadsheet errors that made global headlines, such as the Reinhardt-Rogoff case, where the two Harvard economists released their study into the debt-to-GDP ratios of global governments. And this painted such a dire picture that it prompted many countries to adjust their economic policies to favor a more austere approach. Now, their study was released in 2010, and it contained errors which did not come to light until 2013, when a graduate economics student was attempting to reproduce the results that they had achieved. Now, it turned out that the original calculations omitted 5 lines of data, so representing information about 5 countries, which, if it had been included initially, would not have yielded such depressing results in the first case. And another case is that of JP Morgan Chase, where they lost $6 billion in 2012. Now, what happened there was that an existing spreadsheet was used as the basis to create a new one to model the volatility of trades for a new portfolio. And those calculations involved copying and pasting between spreadsheets. And it turned out that instead of dividing by the average of 2 numbers to calculate the volatility of the trade, the sum of those 2 numbers was used. So dividing by this larger number, of course, yielded a much smaller result. So that made the transaction appear much less risky than it actually was. And that eventually led to a great loss for the company. And there are many more often untold stories of where spreadsheet errors have had dire consequences for those involved. In both these cases, the transactions or the calculations simply lacked transparency. There was no direct visibility into which equations were being used or where input values were coming from and where the results were then being used. And these are fundamental requirements of any tool that's used for engineering calculations. So given all this, we're saying that Excel is probably not the right tool for engineering calculations. So due to the cryptic nature of Excel, how difficult it is to follow calculations, but yet how easy it is to introduce errors that go unnoticed, and the fact that it just doesn't have the computational breadth required for complex engineering projects, we begin to see that Excel is just not a recommended tool for engineering calculations. What engineers need are interactive tools that have the capability to handle the scope of mathematical computation required for today's advanced engineering projects. So when performing calculations, engineers need to be able to describe their problems and to write equations using standard mathematical notations. So whether there's something raised to an exponential power, calculating square roots and logarithms, and using trigonometry, sine, cosine, writing differential equations or integrals, using Greek symbols, whether it's the sum of something, or talking about pi and rho and sigma and all these different symbols. And then once these equations are written, engineers then want to be able to work with them in a natural way. So whether you want to rearrange an equation for a particular variable, or complete the square, apply a trigonometry identity, and on and on. And additionally, such a tool should ideally also capture the thinking process in addition to producing results. There's a lot of richness and value that lies in being able to describe the problem and include diagrams, for example, to state what assumptions were made, or the reasons for selecting certain variables, for example. So including all the thinking as well as stating the problem and going on to solve it and get results. So having a tool that can do all this and more certainly brings great values to engineers. And when we think of such tools, we naturally think of Maple. Maple is a world leader in mathematical and symbolic computation. In addition to high-performance numeric computations, Maple also has world-leading symbolic capabilities. It has over 5,000 functions which cover virtually every area of mathematics. So from calculus to differential equations to statistics, physics, linear algebra, transforms, and just so much more. And Maple enables engineers to analyze and explore and visualize and solve mathematical problems all in one intuitive environment. And the great thing about the environment is that the interface enables engineers to interact with it in multiple ways. So whether they want to drag and drop from the various palettes available, or whether they want to just dive right in and use the sophisticated Maple programming language. And when using Maple, all the technical knowledge of a project is captured in one electronic form. So that can combine text along with diagrams and images and assumptions and references and sound, along with all your calculations and results, all into one intuitive and interactive project document. So Maple enables engineers to solve technical computation problems much faster and in a more intuitive way. I'll now hand over to Stephen, who will walk us through some of the specific differences between Excel and Maple and show us how Maple is a far superior tool for engineering calculations.
Thank you, Shola. Now that you've heard a little bit about Maple, let me begin the comparison by contrasting the core computational capabilities of each of Excel and Maple. Let's begin with Excel. Excel is a business tool which has evolved to handle some non-business calculations. Its function library includes basic math and engineering functions, for example, trigonometric functions or elementary statistical functions. But this doesn't come close to covering the scope of calculations that are needed for a typical engineering project. It's possible to automate Excel using macros or external scripts, but these are compelled to manipulate the spreadsheet cells directly and write the data in place in the worksheet. Finally, Excel has a hard limit of approximately 1,048,000 rows and 16,000 columns. So there's a ceiling on just how large your worksheet is allowed to get. Let's move on to Maple now. Maple has over 5,000 functions covering virtually every area of mathematics, including calculus, algebra, differential equations, statistics, linear algebra, geometry, and integral transforms. As I mentioned, Maple's roots lie in symbolic computation technology, which means that it's able to draw upon the very best techniques in both numeric computation and symbolic computation to offer you hybrid algorithms that give you the best of both worlds. Maple has world-leading algorithms for deep computational problems such as integrals, ordinary differential equations, partial differential equations, and differential algebraic equations. For each of these types of problems, it's possible to request either a numeric approximation to the problem or a symbolic solution if one is available. Maple also has a set of efficient tools for high-performance computing and large-scale problem solving, including algorithms that utilize a distributed computing approach, grid computing approach, and can dispatch Maple computations over multiple threads on your machine. Finally, Maple has a rich and expressive programming language that allows you to provide powerful high-level descriptions of scientific and engineering problems. Let's move on to the subject of mathematical notation. Excel has a flat table structure. There's no natural way to document the structure of computations in an Excel workbook. It's very difficult to represent three-dimensional data in Excel. You can use the VLOOKUP command to index through data to simulate dimensions when you have more than 2 dimensions. But it's costly and more tedious than it needs to be. The syntax for variables and mathematical expressions in Excel is obscure. Given this example, it's not clear to me what these cell references correspond to and exactly what would happen if I were to move the row that contains the data referred to in these cells, whether this would update, whether I would have to go back and change it. The computational dependency chain in Excel is just opaque. You have to jump between cells to track the flow of inputs and computations. And as I mentioned, if you restructure your document, you had better hope that all of the references have been corrected, but you have to probably go back and make sure that that's the case. By contrast, in Maple, you can write equations and formulae in an intuitive and comprehensible manner. And you can, when writing these, you can use standard mathematical notation as you see it in textbooks. For example, this sum you see here, part of a differential equation, is represented exactly how it would be represented in Maple. And if you build it graphically using the Maple tools for doing so, not only do you not have to know the Maple commands for differentiation, which these refer to, but you can just use this. The input is as you see it, and it's a live expression which you can immediately use to compute. Because this documentation is based on standard mathematical notation, it's easy to see where the input values are coming from and how they're going to be used. Maple offers a set of tools for easy entry of this textbook-style notation. And container structures in Maple, such as vectors and matrices, are rendered in the form you'd expect given textbook notation. So a matrix in Maple is a two-dimensional array of numbers, as you would hope for. Let's discuss now some topics specific to scientific computation. Excel does have some tools for unit conversions, but these require you to provide the thing you're converting, the unit system you're converting from, and the unit system you're converting to all up front. So in this particular case, we provide the data via a cell reference, and we explicitly state we're converting something in feet to something in meters. Excel has no built-in support for tolerance computations. So if you want to compare, for example, computed value against some reference value and branch on whether or not the computed value is within a certain tolerance of the reference value, then you have to do that yourself with a little bit of math like this. What we'd really like is if there was a framework already there for that. By contrast, in Maple, you can compute naturally with units, including units from different unit systems. For example, in this case, I've specified up front that I want all of my units to be expressed in the computed results in the SI system. So though I've entered a unit in pounds and multiplied it by 14 meters per second squared, you'll notice that I get a result in newtons. And notice that it's also clever enough to recognize that when I have a unit of mass times a unit of acceleration, that the result should be a unit in newtons, and that is a force unit. It's possible to extend our units framework to include custom units or systems. So if you have a new length unit 2 times a foot, which you want to be your base unit, it's possible to do that and express everything in terms of that unit. Finally, Maple has built-in tools for tolerance analysis, so it's possible to express the error associated with a given measurement and then have that error propagated through the computation using the natural rules for worst-case error propagation for addition and multiplication. An essential goal whenever you're embedding engineering knowledge inside a computational tool is having a verifiable development path. With Excel, it's difficult to add notes and comments to existing workbooks while ensuring they're seen. If you have a colleague who shares a workbook with you, which you want to extend, in general, it's a difficult task to do so in a way that guarantees that your changes will be noticed. As we've already discussed, the fact that the dominant paradigm in Excel is referring to data in other cells via cell reference, $A, $1, or whatever, obscures the mathematical semantics behind that formula. It's important to note that Excel does not adhere to the IEEE 754 floating point computation standards for denormalized numbers, positive and negative infinities, and not numbers. What this means is that the core floating point arithmetic on which you're basing your engineering computations is a different arithmetic than you find in most other implementations of floating point arithmetic, including the ones in, for example, ANSI C. This is a very important difference especially if you're talking about corner cases which may not arise in a typical test scenario, but may arise in the field. Because Excel's functions are built in, you can't audit them, and you have to trust that they were implemented correctly. Moving on to Maple. Maple has a rich document format which allows an intuitive combination of expository text and live mathematics. As we've already talked about, it's possible to express formulas and equations in natural syntax that you would see in a textbook or a paper. Maple's floating point model is compliant with the IEEE 754 floating point standard, and many Maple library functions are written in the Maple language, an interpreted language, so their implementation can be easily exposed for auditing directly in a Maple session using built-in tools. Once you produce data, of course you're going to want to show it to people, and that brings us to the topic of visualization. As I mentioned earlier, Excel's roots are as a business tool, and it therefore contains many tools for visualizing data for business calculations. For example, bar graphs, line graphs, pie charts, histograms. And these are all fine, but it is difficult in Excel to produce a data visualization that does not fit one of these existing built-in graph types. In particular, there is no support in Excel for plotting three-dimensional data on three coordinate axes, which is a very natural thing to do if you're trying to visualize a surface or if you're just trying to visualize the behavior of three variables in a system. By contrast, Maple was designed from the beginning for visualizing mathematical functions and scientific data in many coordinate systems. It contains user-friendly tools for creating rotatable 3D plots and parameterized plots with slider controls for setting parameter values, meaning you can have multi-dimensional data and you can adjust the sliders to vary parameter values and see either two-dimensional or three-dimensional visualizations that result from applying those parameters to your underlying mathematical model. This can offer you a deep insight into the behavior of the system for different combinations of parameter values. In addition to visualizing the data you've generated, you're very likely to want to pass it off somewhere and do something with it. And that brings us to the topic of connectivity. Excel has no built-in connectivity with other engineering tools, such as MATLAB or CAD systems. And there's no way of moving computations as computations out of Excel into an open format. It's possible to do data exchange with Excel, meaning you can pass out the computational results. But that frequently requires exporting the data as a comma-separated value or tab-separated value, and then importing it into another environment. And you don't gain any access in that context to the original computational logic, to the math behind that floating point number that you've generated. By contrast, Maple has a rich suite of tools for automated code generation, meaning you can start with a program you've written in Maple, and you can transform that program in many cases to a whole suite of languages that we support, including C, C#, Java, MATLAB, Perl, Python, and Visual Basic. In addition to this, we offer what we call the Open Maple API, which is a programmatic interface to Maple from other computational environments. So I can write, for example, a program in C, which utilizes the Open Maple API from within my C program. So my C program will dispatch a computation to Maple, a high-level mathematical computation, for example, return the result to C, and do something with it. So you can gain access to the high-level computational power of Maple from within an existing programming environment. Maple has a package for import and export of data from Excel workbooks. So if you have existing data in an Excel workbook, you don't even have to export it as CSV or anything else to incorporate it into Maple. We can read it directly. Maple has built-in connectivity with MATLAB. This connectivity allows bidirectional data flow with a live MATLAB session. So if you have existing MATLAB scripts, you can launch a Maple program, dispatch computations to MATLAB, and incorporate the computed data back into your Maple session. Finally, Maple offers connectivity to several important CAD systems, including Inventor, Siemens NX, and SolidWorks. So let's imagine you've built a tool which encodes some important engineering computation, and now you want to share it with somebody. Maybe a colleague, maybe a customer. This person may or may not be interested in the implementation of your solution, in the logic, for example, of your algorithm. It's possible this person will be very interested. It's also possible that this person wants to use your tool as a black box, pass in some parameter value inputs, and either see some numerical results or possibly some visualizations. What would be ideal is a tool that allowed both of those, the ability to audit the algorithm underlying your implementation at the same time as allowing the user to treat the solution as a black box, enter some parameter values and perform some computations and see the results. So let's again start with Excel. Well, when we talk about entering parameter values, in Excel, freeform input components are limited to text fields. If we want to talk about redistribution, if you want to share an Excel workbook with somebody, the main way to do that is to share the Excel file. So you put it somewhere on the web or you email it to somebody, and of course you assume that that person must have Microsoft Excel. Now that's, given the widespread nature of the Microsoft Office suite, that's a very common situation, but it is not a universal one. Not everybody has it. By contrast with Maple, Maple has an infrastructure for building interactive documents with custom user interface components. What this means is once you've written, for example, an algorithm in Maple, you can put that algorithm behind a button so that when you click that button, you read in some number that the user has entered, pass it into that algorithm, and then update, for example, a plot of the data and transform that live. If you have prepared your worksheet using these interactive components, you have two deployment solutions that you can use. The first that I wanted to talk about is you can deploy your interactive document without any further transformations to users over the web using our MapleNet tool. When you take your .mw file and put it on the web on a MapleNet server, it's instantly transformed into an interactive web page in which the user can enter values in the input components as HTML components and just click buttons to submit them and see the generated results. Additionally, Maplesoft offers a tool called the Maple Player, which is freely available from maplesoft.com. And with the Maple Player, you can take an interactive document and run it locally on your local machine at no cost. The experience of using the Maple Player is not as rich and expressive as you get with using the full version of Maple, naturally enough. But you're still able to enter parameter values, perform computations, and see the generated output. The point here is that Maple's infrastructure for deployment offers you a clean and simple visual interface which enforces a distinction between the experience of the author of the tool and the experience of the user who's simply trying to consume the tool and use it to generate some data. However, the engineering knowledge built into the tool is still auditable by any user of the interactive document. So now I'll pass it back to Shola to summarize the differences between the two tools that we've seen in the last few slides.
All right, thank you, Stephen. Now, we all know that engineers today are under increasing pressure to deliver better products in less time and at lower cost. Therefore, it's becoming more and more important to use the right tools to get the job done the first time. So what engineers need are robust and powerful interactive mathematical systems, so tools which are dedicated to solving these complex mathematical problems and therefore have an inherent knowledge of multiple mathematical disciplines, and also a tool that can capture the thought process and then go on to document the entire project. So from defining the problem to stating assumptions, going on to perform calculations and presenting the results as well. By using the right tools, engineers can minimize errors that lead to project delays and reworks. They can also control rising costs and avoid unexpected outcomes. So switch to Maple and don't let the use of inadequate software jeopardize the success of your engineering projects.